Hello everybody. Today we're going to be talking about the direct comparison test, which is a topic in Calculus 2, as well as a topic in real analysis if you ever get that far in mathematics. The direct comparison test is a way to determine the convergence of various different things. So usually you'll see in terms of improper integrals, series, and sequences, but it has a very large swath of applications outside of that as well. So what we're going to do is let's just write down. It's used to check divergence, and it's used to check convergence, which actually makes it a very powerful test, although it's one that only works if you're particularly clever. So let's say that we have some series. The sum of a sub n, where we'll always say that a sub n is greater than or equal to 0. This may not always be the case, but I urge you to figure out what you would do if a sub n can be less than 0, with n equal to 1. Okay, and we want to know if this series converges or diverges as n approaches infinity. So remember that an infinite series is just a sequence of partial sums. So it's going to be, sum s1, and then it's s2, and then all the way off to infinity. It's just a sequence of partial sums. So we want to know if this sequence converges or diverges. Now, for infinite sums, this could be really tough, particularly if there's no closed form. So what do? Well, there's a lot of series that we know already whether they converge or whether they diverge. So like, for example, this n equals to 1 to infinity of r to the n. This will converge. I'll just write a c. It'll converge if r is strictly less than 1, and also this, we'll say that absolute value is strictly less than 1. And it will diverge if the absolute value is greater than or equal to 1. Which is, this is a really useful one. So, you can use this in your own personal problems. Another one that you'll be seeing used a lot is 1 over n, the very famous harmonic series. So this diverges. So we can use it to compare to divergent series. And then another very important one is 1 over n squared, and this one converges. So, and this also will be the same for n cubed, n to the 4th, n to the 5th, as long as the exponent is greater than 1, strictly greater than 1. Now, we know the values of these, and actually proving whether or not these converge or diverge, these were quite direct, very, very easy and direct methods. So now, if we have a sequence that's tougher, how are we going to do it? Well, let's look at a graph. So let's draw out a graph like this. That's supposed to be a straight line. Now, say that our function, let's see, this is our series that we're trying to find. Say it goes like that. You might be inclined to say, oh, this is a divergent series. But who knows? Maybe, it peters off and then converges. But what we can do is we want to take series that we know and we want to compare them. So say we know that this green series that I'm going to draw right here, say we know that this diverges. We know that this diverges. And not only this is our series of a of n. This is our series bn. We know that the series that we're trying to find, our an, well, we know that an is just our sum is just bigger than our other one. So we can see from this graph that just our one that we're trying to find, an, it's just much bigger than bn. And we can represent that in this sum. And if we know that bn diverges, which means that bn grows and grows and grows to infinity, that means that an has to be bigger than, bn as it's growing to infinity. And that means that an must also diverge. Similarly, say that we knew that this was actually what was happening. It was to peter off like that. And we had another series. Say we had some series that looked like this, and this is Cn, and we know that Cn is a series that converges. And we said that the sum of Cn is always bigger than the sum of our ANs. Say that this was the case, and we knew that this was converging. Well, that means that this has to converge to some finite value. Like the sum will always be less than this value. And if our AN sum is always less than that, well then, if this is less than some finite value, this also must be less than some finite value, which means that both of these will have to converge. So then that will mean that this one converges. Now, let's write this out in a way that maybe makes it a little bit easier to fully grasp. Oh, I'm running out of space. Hopefully I have enough space to do an example. If we're writing this out, if we say that our sum, an, is less than a convergent sum, then that means that an is convergent. However, if we say that a divergent sum is less than our an, well then that must mean that our sum is divergent. And remember, this is just because of that graph that I just showed you, where this is some finite value and we're always less than that, which means that we have to converge to maybe that value or something smaller. And this is going off to infinity, which means that this one also has to go off to infinity if this is bigger at all times. So let's just do one little quick example using this. So let's say that our series was the following. Let's say it was equal to 4 over 5 minus 1 over n squared to the power of n. N squared, and then let me just make sure that plus 1. Okay. So say we had this series right here, and it starts at n is equal to 1. So what are some of these numbers? This is going to be, 4 over 5 minus 1 over 2 plus 4 over 5 minus 1 over 5 squared plus ... Who knows? I'm not going to try to integrate that crap out. Is this series going to converge or is it going to diverge? Well, let's look. This portion right here, this is 4 over 5 minus 1 over n squared plus 1. Well, for all values, oops, that's not squared, that's to the power of n. For all values, right, 1 over n squared plus 1, this is always bigger than 0. It's going to approach 0, but it's not going to reach 0. It's always bigger than 0. So, If this is always bigger than 0 and we're subtracting off a number, that means that this portion has to be less than 4 over 5 to the power of n. And remember, that's just because this quantity is going to be bigger than 0. So if we're subtracting off a number, we're subtracting parts off from 4 over 5. So since we keep subtracting off portions of 4 over 5, it's always going to be less than 4 over 5. Well, that means that we can take our series and we can say that, okay, what we had, 4 over 5 minus 1 over n squared plus 1 to the power of n. This goes off to infinity. N equals 1. This has to be less than, and it's got to be less than what we just found. It's got to be less than, as you approach infinity, n equals 1, 4 over 5 to the power of n. And look at this. This is the same as one of the series that we said we know whether it converges or diverges. This is r, right? So we would say r is equal to 4 over 5, which is less than 1. And because we have that, we know that this series here converges. It converges to some finite value. So we can even find out what that value is. It's going to be like 1 over 1 minus 4 over 5. Am I doing that formula correctly? I might not be doing that formula correctly because it says it's going to converge to 5. I don't know if that's the case. Who knows? Not me. But whatever this value converges to, this is going to always be bigger than this. And because this is always going to be bigger than this, and this converges to some value, that means that this series right here is convergent. And just like that, you've proved that you have a convergent series. Congratulations.